All right, so let's get started. George, quick question. Is the camera on?
I think so, yeah.
So we were planning on recording this and streaming it simply because this is the first time we've done this. We know there's a lot of things that we're going to be working out, and we'll be able to review it later on and see what we can do. Now, if anybody has objections to that, because your audio, when you ask questions, will be recorded, please say so, and we'll be glad to not do it. Or everybody's okay? Everybody's okay with that? All right. So a couple of preliminaries. First, thank you very much for registering for this. This is brand new. George started developing this 6 months ago, so we are, as we affectionately call it, on the bleeding edge, making mistakes, learning, and developing something that we think is going to be pretty fantastic. And so we're delighted that you all registered for this today, and we appreciate it. And I appreciate those of you that took the time to complete the survey, so it gave us a better idea of what your backgrounds were and needs and expectations, and hopefully we'll meet them today. Which brings me to the point of this workshop. It's for us to teach you and get you to be able to do what we think is a pretty exciting opportunity and package, but please tell us if there are things that you don't understand or if we've done ways that are counterintuitive or you'd like to see a different way. Just let us know and we'll build those changes and features into the package. So we're going to do a combination of slides. I'm going to cover theory and material about what we're trying to do, and George will run the R code that shows how we do it in netdiffuseR, which we've gone back and forth about how to do this, and that seems to be the best way we think, so we'll see how it goes. So first and foremost, this wouldn't be possible without funding from the National Institutes of Health. So we have a grant to study the global diffusion of tobacco control. That was the impetus for doing these advanced network diffusion models, and they have funded us to be able to do this. So we greatly appreciate the National Cancer Institute and the National Institutes of Health for their support. We also have a lab, the Center for Applied Network Analysis at USC, and people who are in our group, and there's quite a few of them, you can see some pictures on our website, they've provided helpful comments and feedback as we've gone along too, so it's important to acknowledge our team. Okay, so here's a quick outline of what we're going to do. I'm going to talk about some introduction to diffusion networks, talk about what they're like, and then why we had to develop netdiffuseR, this package. Then we have some empirical showcases. There are 3 classic network diffusion data sets: medical innovation, Brazilian farmers, Korean family planning. They come with the package, and we will first demonstrate some of the package features using those classic publicly available data sets, which you may be familiar with. And we will illustrate how you can analyze network effects using netdiffuseR and other techniques. Then we have simulation capabilities built into the package so that you can do different kinds of experiments and agent-based models and whatnot using netdiffuseR in a very quick and efficient way. We'll take a short break. Then we're going to talk about reading data. One of the features that makes this package, I think, really exciting is George has built in features to take data from a variety of different formats and make it a diffnet object so you can work with it. And I think there are people that are going to want to use this package simply for those features. Take a quick break, then we will illustrate the features using the FCTC network diffusion data. We have results for that we've published, and now we'll replicate them in netdiffuseR and go over how to do that. And what that level of analysis now incorporates is multiple networks that are both static and dynamic built into the package. And then finally, we have another study, the social networks and networking study, that has it's more of a cohort-type traditional data set. And we'll show you how you can use netdiffuseR on that kind of traditional basic data set. So that's pretty cool. And then hopefully we'll get this wrapped up in time for some Q&A, questions and answers and whatnot. So, and at any time, please, I grew up in New Jersey for part of my life, which is a state in the northeast of the U.S., and I tend to talk really fast sometimes. So please interrupt me or ask me to slow down, and I'll do that for you. Okay, so what are diffusion networks? Diffusion networks are it's a very unique set of data. And it's unique because you have data on behavior typically from 0 or very low prevalence to very high prevalence, right? Most of our social science data, you may have 1 or 2 years, you have behavior change of 5 or 10 percentage points, but in diffusion networks, you're looking at something over the long term. And that's why there aren't a lot of diffusion network studies, right? Because it takes so long to get that kind of data. You have multiple time points, and you have multiple ways to model the relationships that you're interested in, so it's a fairly complex kind of problem. Your network data may be static or dynamic, right? And you can, so far, we are only treating one behavior at a time primarily. We'll be adding extensions later where we have multiple variables. And because we combine network data and diffusion data, you end up with all kinds of crazy things in terms of the data management, where you have people with network data but no adoption data, and vice versa. And we'll show you how we cope with that. So, diffusion of innovations, it's an old theory. I think it's our oldest social science theory. It's been around for over 100 years, and it explains how new ideas and practices spread within and between communities, right? And we know that there are a lot of factors shown to be associated with diffusion. Economic factors, spatial factors, demographic, biological, you name it. But, of course, the network, it turns out, is very important as well. And I would often argue that you only have a diffusion study when you're actually looking at the network so that you can trace how the idea spreads from node to node, person to person. The classic diffusion study, Ryan and Gross, 1943. I've written about this in the past. Great diffusion study. Set the paradigm for the diffusion model, but they did not collect network data, although they could have, because they interviewed all of the farmers in 2 counties. Diffusion research took off in the 1950s, right, and somewhat in the early 60s, first in developing countries, and then it diffused to developing countries. There were hundreds of diffusion studies done, and then it died off, and we wrote a paper about why diffusion research died off. And it's now coming back to life, I think, because of these the new kinds of tools that are becoming available, and the interest in looking at diffusion over social media. So, what do we know about diffusion networks, and how do we conceptualize the spread of a behavior through a network? And we do it primarily through an exposure model, right? You have an ego, they're connected to a bunch of other people, and as their network fills with adopters, they're more likely to adopt. And so modeling this exposure becomes very important, and it's something that a number of scientists over the past few decades have done, right? Coleman, Katz, and Menzel, classically, back in 1966 in their book, Ron Burt, 87, and so on. Now, one of the major innovations that in part reinvigorated diffusion network research was Ron Burt's publication in 1987 comparing contagion models between social cohesion versus structural equivalence, right? Great classic paper. And the other thing that he did in that research, of course, was unearth the Coleman, Katz, and Menzel data collected in the 1950s and make it publicly available. So that was quite an innovation. And then here's a simple illustration of the structural equivalence hypothesis, right? 2 people can influence one another even though they're not directly connected, because they're connected to the same other people or because they occupy the same position in the network space. So, and then I did my dissertation on diffusion networks, reanalyzing the Coleman, Katz, and Menzel data, as well as acquiring another data set, the Korean Family Planning Study, and discovered something that we call social network thresholds, right? And what is the threshold? The threshold is the number of people in your network that you need to see adopt before you're willing to adopt it, right? So you have low threshold individuals and high threshold individuals. And they may or may not be correlated with whether or not you're an early or a late adopter in the diffusion process. So, and then 1995, I published Network Models of Diffusion of Innovations, to sort of look at all 3 of these classic studies and try to do some kind of meta-analysis and report on all 3 of these classic diffusion data sets. These are the diffusion curves for the 3 classic data sets. You can see the medical innovation data grow pretty rapidly. There was very fast diffusion. Over 50% of the doctors, the physicians, had adopted within 6 months. The Korean family planning data was more of a straight line diffusion, almost a constant in terms of the number of adopters over time. The timeline here for the Korean family planning data is years, so it was 10 years over which the diffusion unfolded. And then the third data set is the Brazilian farmers data set. taking place over a 20-year period, looking at the diffusion of hybrid seed corn in 11 Brazilian villages. And coincidentally, I gave the keynote address last year where I gave a talk on the history of all this diffusion stuff, and then the reporting of that keynote is in the connections that came out just this month that you got when you registered. So we're hitting on all cylinders here, folks. If you're not saying Valenti all day the rest of the day, then you're not paying attention. So what is our motivation for building netdiffuseR, right? And actually what drove us to do this is to facilitate calculating these network diffusion models. Because before you would write code, it would be idiosyncratic to the data set that you were working with, and then you'd export it out to Stata or SAS and do your statistical analysis. And we wanted a platform where all of these different kinds of exposure terms can be calculated quickly and easily and compared. We wanted to be able to easily incorporate both dynamic and static networks into the calculations because increasingly, hopefully, that's the kind of data we're going to get. And we wanted to have good graphical displays of the diffusion process. And one of the most exciting features of this package, I think, are the great graphics that George has built illustrating how the diffusion process occurs. And then, of course, being able to do statistical tests to try to make conclusions about the diffusion process and whether or not it's happening the way we wanted. And finally, we are also building features to integrate network diffusion models with other packages, StatNet, Ergams, Sienna, and so on. So it's, this is everything, the whole kitchen sink we've got going here. And there's one other quick thing I should say that, and I didn't properly do this, that both George and I are at the University of Southern California, which is just up the road here in downtown Los Angeles. We're in the Keck School of Medicine in the Department of Preventive Medicine, and that's where we're housed. Okay, so I mentioned briefly, we had these classic network diffusion data sets. There were 6 actually classic diffusion network studies conducted before 1990. 3 of those studies, the data have been lost. I tried to track them down. Everett Rogers was my advisor, so I worked closely with him, and he told me that he lost the 2,4-D weed spray when he moved from Ohio State to Michigan. And then Rogers also collected diffusion network data when he was a Fulbright scholar in Columbia. Those data are lost. And then Marshall Becker, who conducted one of the greatest diffusion network studies of all time, studying public health officers in Michigan, Ohio, and New York, had all the data in boxes. When he moved from Johns Hopkins University to the University of Michigan, he threw out the data. We look back on that and it's sad, but there was a lot of paper and a lot of boxes, so. All right, but we do have 3 classic network diffusion data sets. The most famous is the medical innovation data collected by James Coleman, Elliot Katz, and Herbert Menzel in 1955 to 1957. 125 doctors were interviewed in 4 cities, small towns in Illinois. They were looking at the diffusion of tetracycline. It took 18 months to diffuse. The highest saturation in the cities was 89%. So they had pretty good diffusion of that. The second one is the Korean family planning data. These were data collected in 1973 on when women in 25 villages in Korea first started using contraceptive methods. And they the prevalences ranged from 44 to 83%, so pretty high in some places, not quite as high in other places. And then finally, the Brazilian farmers, as I mentioned, 11 villages, 692 farmers, and they had even more variation in the diffusion rate across villages, 29 to 98%. And you can see the references for where these data come from. Now, to do diffusion network analysis, the insight is to understand that you need to reshape the data that you have to be longitudinal in the sense that it becomes an event history data set. So I illustrate here with this little toy example. There are 3 people that we interviewed. They have ID numbers 1, 2, and 3, and then we have recorded their time of adoption, right? And for a retrospective study, this is the way you would get the data. Or in other studies, you might store it this way in a wide format. So if person 1 adopted in time period 6 in year 6, we reshape the data, right? So now we have 6 number 1s, and we put in a counter for the year or the time, 1, 2, 3, 4, 5, 6, and then the adoption indicator is 0 for every year they're non-adopters and a 1 for the year that they do adopt. Right? You can see the other examples there. And that's the key insight. Once you reshape the data like that, then you can analyze the likelihood of adoption, the likelihood of having that 1, based on both static and dynamic attributes of the individuals, because you've stretched the data out that way. And this also is known as survival analysis, and we'll talk about a little bit the difference between survival analysis and event history analysis. Okay? So, now to demonstrate this, we're going to use these 3 classic data sets. Like I said, they come with the package. Medical innovation data being the first one. There were 3 network questions asked of the physicians. Who do you go to for advice about this particular medical condition? Who do you discuss these conditions with? And who are your friends? And adoption data were collected by examining the prescription records in all the pharmacies in this town the first 3 days of every month. Okay? So if you were a physician actually who adopted in the middle of February, it wouldn't get counted as an adoption until the first day of March. So the data are skewed a little bit that way. Otherwise, they're pretty reliable. Brazilian farmers data. This was part of a very large USAID-funded 3-country study on the adoption of farming practices. Only for hybrid seed corn did we get a lot of diffusion. And in that data, they asked a number of network questions. Your 3 best friends, your 3 most influential people in the community, the 3 most influential people regarding farming practices, and then the best person to organize a cooperative project. Adoption data were calculated by asking people when they first started planting hybrid seed corn. Okay? And then the third study, Korean family planning data. I think in some ways this is the most extensive. Researchers at the Seoul School of Public Health went out to these villages, interviewed people about a whole bunch of health characteristics, but primarily centered around contraception and family planning. And they asked a number of network questions. Looks like at least 6 of them here. Who do you go to for advice about family planning, general information, abortion, health, the purchase of consumer goods, and so on. And then the adoption data were retrospective. There was a very long schedule actually asking about when they first became aware of, had an attitude towards contraception and the particular methods that they use. Yes, sir.
Did they go out and ask these altars that were named whether they...
Yes, everybody in the village, that's the key thing. It's not a snowball, it's a census. So they interviewed every woman of childbearing age in the village.
And what if they named someone for advice or family planning that wasn't in the village?
Then they're not in the data.
Then they're out, okay?
Yep.
So only if you name someone who's
Yep.
in this village.
That's right. And that's true for all 3 of these data sets. They're sociometric in the sense that everybody in the community is interviewed or at least attempted to be reached. And there are no ties outside of the communities. Okay? So, I've got a number of versions of the analyses that I've done on these data sets. You look at the likelihood of adoption. If you look at the sample sizes, you can see that now we're no longer at the individual level, but instead we've stretched it out according to time period. So there were 125 physicians. Their average time of adoption was month 6, and so 6 times 125 gets you close to this number of cases that you have here. And the first thing that we do is look at whether or not there is a time effect in the diffusion data. Okay, so we enter dummy variables for each time year along the diffusion. And if you look at the medical innovation data, there is, according to this result, no effective time. With the Korean family planning data, what you see is that adoption occurs late, right? So it's kind of straight and then it jumps up at the end. And the Brazilian farmers in some ways is the most interesting because it's negative. There's a negative tendency for adoption early, and then later on the coefficients go up and become positive. And you can see that in the curve. Now once you've controlled for time in this event history analysis, you can add in individual characteristics of the respondents, right? These are static ones, so whether or not the physician was visited by a detail agent, their orientation to science, their journal subscriptions, for the Korean family planning data, number of sons they had, exposure to mass media outlets that were advertising contraceptives and reproductive health during the time period, and so on. And for the Brazilian farmers, we included incomes, visits to the city, and so on. You can include network variables in the analysis. And then finally, and critically from our perspective, then you include an exposure term, right? And this is the number of adopters in your network over time. And it is a changing variable over time. And in most diffusion studies, that variable will continue to increase over time because we don't have disadoptions. If you have disadoptions, that exposure can go down, but we don't have any data yet where that's the case. Yes, sir?
And it's only, now you're talking about the ego network.
Yes, that's right.
Direct exposure.
Just direct exposure here. And we'll talk about extensions to that in a minute. But this is just direct exposure, the people that you've nominated in your network and when they've adopted. Okay? That clear? That's the basic model and the basic idea. Okay, so now we're going to illustrate how you can do this in netdiffuseR with these classic data sets. We'll start with the medical innovation data. Yep.
Okay, so here I have a script that I share with you. That the first one is called classic long version 7 actually. So it's type.
Oh, so, version numbers keep going up.
Yeah. So most of you are familiar with R, so I'm going to just skip this a little bit. So here I'm just cleaning the working space, right? So in the 4-inch library, because the package, because here we have the survey data set in Stata format. We're going to read it from there and then load the netdiffuser package. So if we run these lines, should have no problem. Then I read the data into R using foreign, right? Reading this data.
Oh, okay. George, can you make the font bigger?
Bigger?
Yeah.
Sure. Is that good?
Almost. One more.
I'm with
One
you.
bit.
Okay.
Nice.
Thank you.
Do you want me to twist it a little more?
It should be.
Okay, so now if I look at the data, we can take a look at it, right? So you can see how it looks like. What we have here. So this is basically one row per individual. So we have an ID, we have a city ID also, which is important for this function that we're going to introduce here. And then we have network nominations data, besides of the covariates characteristics of each individual, right? So there we have the network nominations, right? So this is cross-section data. And in order to read this into netdiffuseR, we use the survey to diffnet function, which basically takes this kind of data where you have network nominations and transform it into a network, basically, and actually into a diffnet object, which we are going to see in more detail later. Okay, why is it useful? So by the way, I think we didn't include it in the notes, but most of the functions of netdiffuseR can be used with raw, we're saying somehow, raw networks. So you can actually use arrays instead of diffnet objects, matrices, sparse matrices instead of using diffnet objects. But the thing is that diffnet objects are like are built in with netdiffuseR, so you have more features if you use them instead of just using the plain matrices. Okay, so here, what's to highlight here? So here we have the functions of it to diffnet. We have the data set. And then we have to identify some the variables. So first, an ID variable for each individual in the network. Net variables, which can be either one or a list, right? A vector of variables that hold nomination data. Time of adoption variable, which is important, right? You can analyze diffusion if you don't have this. And in this case, this is a nice feature, group data. So, for example, here we have that Dr. Medic 1 nominated Medic 2, Dr. 2, right, in City 1. But you also have a Dr. or Medic 1 in City 2. So in order to account for this and not to create networks between people that actually are not connected, we can identify a grouping variable here, which in this case is City. Is that clear?
Everybody got that? So we have all these different communities. Yep, good. Okay.
And Here I'm just, so the thing is that these variables for now have to be integers. Okay, so because the way it codes it, for instance, it cannot be city Atlanta, it cannot be, I don't know, or, so it can be city 1, city 2, city 3. And with this option, I'm just telling the diffuser not to warn me that it is coercing the data into integers, right? So when we run this, we get a nice big
George, can I just ask something?
Sure.
Do we have this data, do we have access to this data?
Yes, it's right there.
Oh, yeah. So actually, this data, sorry, I forgot to mention. So you can access this very same data like this. If you go to your R, and type down Meta Innovations, this is the same data set. It's just a different name, but it's included. So you actually have two versions. You have the raw data, like unprocessed by the diffuser, and you also have the diffnet object.
Right, so this medical innovations data is already a diffnet object and ready to be analyzed.
Yeah.
So you don't have to run the survey to diffnet command with that one.
So it's all like this. So you also have the same with Brazilian farmers and Korean family plan. You have all that included in the package. So once you got your diffnet object, you can print it out and get some details. So this is basically showing you a brief picture of what you have here. So you have average park nodes, 18 time periods. This is a directed graph. Everybody adopted at the very end, and it shows you a list of ahead of what you have in static attributes, as well if you have dynamic attributes here. This is just the IDs of the individuals.
So does everybody have this now, medical innovations diffnet data? If you don't have it on yours?
Yeah, so if you print it like
Oh, did you get the email?
so if you go to the website of the project, which is you should go here to github.com.
Here's the address. You need to go to github.com/USC Canada. THUB.
github.com/USC/netdiffuser.
George, I'm also not, it's the first line, MITT.
Oh yeah, it's because you don't have that file actually.
Okay.
So you have to load it this way.
Okay.
Yeah, actually you can.
Oh, great, good. Oh, you know what, so,
Yeah,
yeah,
that's
that's
the different
already
object and
a,
the other one is
yeah, that's, yeah, you don't need to run that. But if you were to want to run this, I think it's just the net innovations, is that right? That doesn't work. Okay.
But that's.
Yeah, I
Okay.
think we're using Yeah, yeah. You did? What's that? Oh, good. Oh, yeah, yeah.
Some data.
Okay, does anybody else have problem with talking to you first? Careful.
So you've got it.
Oh yeah, you can work with that. but I see that you have the current
So
version.
data and innovations.
You can use that too, but the survey function is new. So it's not in the current version. You can go to the project website at GitHub. GitHub, netdiffuseR, and you will find an instruction how to install it. Actually, I didn't slide it. Yeah.
Okay, good.
Yeah, actually, have fun with the actually. If this doesn't
That
work,
seems to
then
have more
try
trouble.
with the terminal. So the terminal type R.
And it seems like something that will work
Yeah,
on
like
a Mac machine, doesn't necessarily.
If this doesn't work, just copy paste this time.
Mhm.
Right, it should work. So anybody else? In order to move forward, I just recommend you to, if you don't have the time to install, we can take it out later because there are specific cases, right? But the thing is that so the data and then diffusion of so the Korean family, the Brazilian farmers, and the American innovation data is all built in the diffusion. So later on, you can even if you don't have tons code, you can check it out. The diffusion objects that are generated for these data sets. Okay? So once you imported your diffusion object, you will see something like this. Okay? Which is, we're going to talk a little bit more about it later. And here you can actually, this is R, so you have methods, right? You can plot it, you can summarize it, and a bunch of stuff. And here we have the summary version of this.
So summary is nice because it lists each one of the time periods, the number of adopters at that time period, cumulative adoption numbers, and then the proportion, right? So you can see the growth, the rate at which diffusion is occurring, the density of the network, and then Moran's I, which is a coefficient of contagion. Moran's I calculates the extent that two nodes that are neighbors are engaging in the same behavior at the same time. It's kind of an old geographic statistic.
Yeah, and also shows you the censoring of the data.
Oh, right, the left censoring, the number of people who adopted before we started the diffusion process, and the right censoring, the number of people who would have adopted after we collected the data.
Can you repeat what the Moran's I is again? Can you just
So Moran's I is a calculation of whether or not adjacent nodes are engaged in the same behavior.
Okay, so now here becomes the fun part. So in the diffuser we have the exposure function. We will see this more in detail later. But this basically using a different object allows you to compute straightforward exposure for each individual for each time period, at each time period. So if I run this by itself, I get a matrix of size n times t. It shows me the exposure for each individual at each time period.
At each time period. So this exposure matrix is every individual at each point in time, the proportion of their neighbors, their alters who have adopted. And you'll notice something that happens when we do the net diffuser object. We've changed the ID numbers and added the group variable information into the ID. So this now indicates city 4, person 30. And we've done that because then we can have all of the data from all the cities in one diffnet object. And we know that they can't communicate with each other, but it's all in one object. So that can easily be imported to run a structural zero ergo, for those of you who know that.
Yes, and actually you can also take into account the group differences. For example, here I'm also continuing exposure, but here I'm using a more refined version of it, in which I'm using structural equivalence exposure. which instead of using the graph itself, it calculates the structural equivalence matrix for each time period, and uses that as a graph, as a social network to compute exposures. So it's a value graph. And here, in order not to do it for the, compute the structural equivalence for all the set of all the pairs of nodes, I'm telling here in the diffuser that actually they are grouped. So when I specify the group RC, which is a variable that is inside of an object, this is going to take into account that, so it's going to be a faster computation, and it's going to leave zeros between the individuals who don't share city, in this case. Was that clear? No? We are going to review this later again, so, but this is just to have an idea of the capabilities that we have here. Yeah, and the next thing is here that just like a data frame in R, I'm assigning new objects here. So this is a new dynamic variable actually, which we can assign this way. And again, another. Then this warning is only telling us that since we're using structural equivalence, we have to have a value graph. So by default, netdiffuseR is changing the option values to true in this case. You can get more help, more information about this function if you go to the help file here. So we have actually a bunch of options for each of this. We have graph, community adoption matrix, and you can actually compute attribute weighted exposures, use alternative graphs, computing on outgoing ties or incoming ties, value it, you can have it normalized or not. When you don't have it normalized, it's a count. So instead of telling you what proportion of your equal network has adopted at each time period, it tells you how many individuals have adopted at each time period. That could be useful too. Yeah, so you can then later export your DiffNet data as a data frame using this function. We're going to see this more in detail later. I'm going to run this line here. Yeah, and take a quick look at it.
So now that we've done our calculations in netdiffuseR, we make it a data frame so that we can do statistical analyses on it.
Yeah, and here, see, we have, this is actually a dynamic because now we don't have only 125 individuals. We have, observations. We have 2,000 because it's by the time periods, number of vertices in the graph. For each one of these observations, we have the cohesive exposure, which is the portion of the unit who have adopted, and the structural equivalence exposure for each time period.
Now, does everybody understand why we have 2,250 observations? We have 125 people, and we have 18 time periods. Multiply those out, you get 2,250.
Now I'm just going to run a couple of lines here so I don't want to discuss this with some.
Yes, so now what we're going to do, we've got our DiffNet data, we've converted it into a data frame with 2,250 cases. Now we're going to convert it to, we've got it set up over time. We want to do event history analysis. Remember when I showed you that table? We have zeros and then a 1 the year they adopted and no more after that. We need to get rid of all of those post-adoption cases, right? So we're going to do it with this command right here. We're going to create the adoption variable and set it to the time period that they adopted, and we have equals. Right. Oh, okay. So we figure out which time they adopted, and then we look at their time of adoption data and take all of the cases that are less than or equal to their time of adoption case. So we've gotten rid of all those post-adoption cases. We now have a data frame of the event history network diffusion data. And we can now do statistical analyses to determine if our variables of static and dynamic exposure are associated with adoption. Right? So there's how to input a statistical regression formula in R, which many of you may be familiar with. Right? So we specify what the equation is, what are the variables that are associated with adoption. In this case, we're going to look at the professional age, the journal subscriptions, orientation to science, whether or not they were contacted by a detail agent, and then cohesion exposure and structural equivalence exposure. What Ron Burt did nearly 30 years ago, but we do it in 4 or 5 lines of code. Did you run it? Do we have results? No.
Now we have the model.
And now we have the model. Here are the results. Dummy variables for the time periods, and then our variables. Age is associated with adoption, journal subscriptions associated with adoption, orientation to science, contact by detail agent, no, cohesion exposure, no, structural equivalence, no. For those of you who read Ron Burt's article, he did find an effect of structural equivalence, but remember, he exponentiated his structural equivalence graph to change the weightings, and he did it separately by city, and I'm not sure that's the right thing to do.
And actually, now that I remember, you can actually also replicate this because we can also take to the power the structural.
Yes, we can do that too.
So you have that option when you compute structural equivalence, you can specify the B variable, which is the
weighting on the structural equivalence to either contract or expand the social radius of observability that individuals have. Okay, and now, so let's do the plot, right? So this is really cool. We ran plot adopters. If you run plot underscore adopters, you'll get this graph. Now you get our diffusion graph, the cumulative adopters, and the number of new adopters at each time point, right? How long did it take Ryan and Gross to make their diagram? I don't know, but we can do it now in 1 second, which is, again, amazing. And then we also have plot diffnet, which I think is even more amazing. So here, what you get is a plot of the network in each time period, and then the adopters are colored as they're empty if they're non-adopters, red when they newly adopt, and blue if they're a continuing adopter. So now that's a little hard to see because you have all 4 villages, all 4 cities at the same time over 18 time periods. So you can do it where you just select one city, and you can do it where you select the number of time periods. So the plot diffnet has an option for the number of slices that you want to see. So you can just look at time periods 1, 6, 12, and 18, or 1, 5, and 10, whichever ones you want. So that slices option gives you the opportunity. Now that looks a little better. You can just see time period 1, 6, 12, and 18. And can you do it just for city 1, 2, 3, 4? Just whichever one. Oh, that's time period.
cities.
City, yeah.
Yeah, for city will be something like this.
Actually, do you want to show the no network graph real quickly? Can you do plot diffnet no 16 if you already have it loaded? Oh, there it is. Yeah. No, just this one, the plot diffnet. Okay, so this, if you can see it a little bit better, how about you zoom in real quickly, Georgia? So this is a little toy data set that we collected from the network class that I teach. There's about 35 students in the class, and I simulated diffusion of the data just by assigning adoption times to people that they were connected to via sort of visualization. So there's your first adopter at time period 1, and then you can see when you go to time period 2, that first adopter goes from red to blue because they're continue to adopt, and the new adopters are these 3 here in red. Then when you look at time period 3, now you have the 4 continuing adopters, and these are the new adopters in time period 3. And then time period 4, 5, 6, and then 7. So you can see visually the spread of the behavior through the network. Right? And so I think that's great. That's a really nice plotting feature. And when you just have one network, you can see it a lot better than when you have a whole bunch of different networks.
Here's a question.
Sure.
So how did those, that triad that's not connected, how would they adapt?
They would adopt by some external influence.
Yeah.
And so we typically think of if you don't adopt via network effect, then there's something external to the system that's influencing you. From a communication perspective, we usually think of it as a mass media campaign or some kind of promotions. But it could also be from labor exchanges. In the Brazilian farmers, I modeled visits to the nearest largest city, cosmopoliteness, as being an influence on diffusion. And if you go back classically to the Bass model, remember, you have 2 different components of the adoption process, the internal influence and the external influence. And the Bass model gives you estimates for both of those.
Right, and we usually think, we were discussing this with Tom, if you don't get any diffusion outcomes here, it's either because you have the wrong data, right? Or because there's something else going on.
Something else driving the process.
But
Yeah.
this kind of, it's hard for us at least to think that there's not a network like effect there, because somehow you get information, you're embedded in the system. It's not like, so if you don't see any effect, it's probably because you have a different network.
Okay? All right, so that's the medical innovation data. We also have the Brazilian farmers data, which we could show you real quickly how we calculate that. You have the code. It's the same process. You're running survey to DiffNet, converting it to a network diffusion object, calculating exposure terms, cohesion, and structural equivalence, and then turning it into a data frame, getting rid of the post-adoption cases, and then estimating the model to see if you have network effects on adoption. And it takes a long time to generate the Brazilian farmers' DiffNet plot, so I did it here and put it in as a slide, because if we did it here, we'd have to wait for it to fill the screen. It would take a little bit of time. So here's the Brazilian farmers' data. Again, we have dummies for all the time periods, and you can see that there are some significant time periods when adoptions pick up. Again, it's late in the process, what we saw. Visits to nearest big city is significantly associated with adoption, as you would expect. News is one of the items about how much you pay attention to the news and whatnot. Then mass media exposure, not associated with it. Cohesion exposure, yes, and structural equivalence exposure, yes. So controlling for a lot of things, we see a contagion effect here for both direct ties and structural equivalence ties. And we always expected structural equivalence to be stronger in the case of Brazilian farmers because the farmers are like businesses. And Ron Burt's original argument with structural equivalence is people are going to be influenced through their structural equivalent alters when they're in competition with one another. If they're 2 firms, for example, competing for the same customers. And so in this case, Brazilian farmers, they may be viewing each other as businesses and monitoring their behavior that way. And we do find stronger coefficients for structural equivalence than cohesion in these data.
And we usually see this in some other data sets that we're trying it out.
Yes.
So
Yeah.
one is it's very important to compute.
Yes, yes. It's an important mechanism. And the fact that we didn't get cohesion in the medical innovation is not surprising to me. One of the persons that did reanalyses of the medical innovation was Christoph Vanden Buell. And he went and got the journals that were in the 4 cities in Illinois at the time of the data collection. And he entered that as a new variable and finds significant effects for potential exposure to that advertising, which I thought was a very interesting finding because the funders for the Coleman, Katz, and Menzel study were Pfizer Pharmaceuticals, and they wanted them to evaluate their media communications. And Coleman, Katz, and Menzel said, yes, we'll be glad to do that, but we're going to turn it into a network study at the same time. So it's an interesting finding that in some ways validates the kind of theory that we've been building over the past couple of decades. Okay, and do you want to show Korean family planning? That would be the last one, right?
Sure. Yeah, and one example for one feature here. So different, we can treat different objects as arrays as well, right? So in this case, for example, since we don't want to plot all the villages for Brazilian farmers, here Tom is actually subsetting, creating a dichotomous vector, a logical vector for only villages, individuals in villages.
Only individuals in village 10. So looking at one village.
Yes, and we are accessing to this attribute in a different object and then creating a logical vector. And then you can subset this way, indexing the different object using a logical vector, for example. And here we are plotting all these slice numbers. And there you go.
Right, so see that, we've got this gigantic data set, we have 20 time periods and 11 villages. Now we're just going to look at one village at one point in time and see where the new adopters are and where the continuing adopters are. Okay? So these are the classic data sets. There's more analyses to be done on these if you're so inclined. We're pulling all of the network data in. You could look at just some particular specific networks. In the Coleman, Katz, and Menzel study, Bert only found contagion effects for discussion and advice and not friendship. And he found it early rather than late. So all kinds of things like that can now be done pretty readily and pretty quickly, which have not been fully explored at all. Oh, there's the Korean family planning data, yes. And what did we get? And we get cohesion exposure for family planning, but not structural equivalence, right? And to me, that's perfectly logical, because I'm going to get information about the contraceptive use by my peers via talking to them, right? I can't tell whether or not they're using contraception, and I'm not in competition with them to use it. I get information, and that information changes my behavior. So theoretically, we're getting the results that you would expect.
Can you clarify that?
Yes, so we have two competing mechanisms right now. I get influenced by my peers via our direct communication. You tell me something about the topic and that informs my behavior, and so I engage in it. The other mechanism is structural equivalence. You and I occupy the same position in the network, and we don't talk to each other, but I know that you're in the same position that I am, and I monitor your behavior, because when you do it, that sends a signal to me that it's time for me to do it. So one example is two assistant professors, right? Assistant professors look at what other assistant professors are doing and model their behavior because they're in the same position and potentially competing for the same slots. So in the case of Korean family planning, I don't view that as a competitive mechanism that would drive behavior. For me, it's the sharing of information, how to get the methods, what kinds are the right ones to use, and so on and so forth. So it's diffusion through the network. Whereas with structural equivalence, it's diffusion because of the network. Does that make sense? Okay. All right. So those are the classics. We're building up diffusion theory. They're built into the package, and we've given you a little bit of demonstration of the kinds of things you can do. With the very few lines of code, there's a lot of analyses that you can do, right? Any other questions about that? No? Good, okay. So the other feature that we want to highlight is how to simulate diffusion, right? Because there's a lot of theoretical things you can do when it comes to thinking about what's driving the diffusion process, running agent-based models and simulations, rather than doing empirical analyses, right? Why go through the trouble of going out and collecting all this data when you can create it right here on your laptop? So one of the things that we have done quite a bit of in network diffusion studies is running simulations comparing seed nodes. Who are the first adopters, okay? And three conditions that we've looked at a lot are looking at opinion leaders versus randomly selected seed nodes versus marginally selected seed nodes, right? Those that are on the margins or the periphery of the network. And so, let's see, what are you going to do first, George?
I sent you the presentation.
Oh, is it in here? Oh.
Yeah. In the meantime, so we're going to now use the file that's called, that has a last name called simulations.rmd. I don't know if you guys are familiar with R Markdown. So R Markdown, okay. Those who have used it, it's a very nice thing that you can, a package that you can use in R that allows you to create documents that have R code built in. So you can actually like write down a paper, a presentation, as I have here, using R Markdown. And the nice thing, the thing is that all the presentation here, all the outcomes that you see, it's actually run directly from R. It's not like I copied and pasted it, so it should work. That's a good thing. Okay, so.
Do you want me to pull it up in R, or?
No, I haven't.
Oh, you had it,
I have
okay,
right
right,
here. So,
right,
yeah,
right.
so, okay, so what we're going to do, just a quick overview of the concepts that we have been looking at. So exposure, Tom already explained it, right? We have threshold, which is the proportional number of